Hi, everyone. Welcome to WQRF's November webinar special. My name's Lilia, and I'm the project coordinator here at WQRF. I want to give a special thanks to Pentair Water Sciences for sponsoring the entire poster contest at the WQA Convention and Expo. We're grateful for their support in making this scholarship possible. I will email you a recording of today's webinar, but you can also visit our website at wqrf.org/webinars to see all of the recordings. Tihitna Mulugeta is our presenter today. She will highlight her research on how grinding techniques affected absorption of PFAS in rapid small-scale column tests, also known as RSSCT, the role of material preparation on prediction accuracy, and the influence of different water matrices on RSSCT accuracy. Tihitna has earned a Bachelor's of Science in Civil Engineering from Haramaya University in Ethiopia and a Master's in Civil Engineering from the University of North Dakota. Currently, she is working as an Associate Civil Engineer at EVS. Her research focus at University of North Dakota was on understanding the effect of ion exchange resin preparation on PFAS absorption in rapid small-scale column tests. So with that, I will turn it over to Tihitna to begin her presentation.
Thank you, everyone. It's good to thank you for joining this webinar. And today I will be presenting the impact of resin grinding on per and polyfluoroalkyl substances adsorption in RSSCTs. My presentation I will be covering the introduction about PFAS and some literature review, or it's like more a motivation for this study. And we will have also the objectives, material and methods, and we will go through the results and discussions. And also, of course, I will be highlighting the limitations and the future work directions. And I will be finalizing my presentation with acknowledgement for which helped me for this study. So here I will start just by highlighting what are PFAS, or which are commonly known as forever chemicals. Like those are man-made chemicals which we have been using for so long time. And the main feature of these chemicals is there is a strong carbon to fluorine bond which induces, or which makes them have a unique physiochemical properties that makes them highly stable to the ground, to the environment, and makes it hard for the degradation of these chemicals from our environment. And because of these issues, the US EPA has set a maximum contaminant levels of these chemicals, which specifically for two of these chemicals, like perfluorooctanoic acid, PFOA, and PFOS, which is a sulfonic type of PFAS, to be up to 4 ppts. So here on the picture, you can see, like, depending on the head group or the hydrophilic polar head group, we may have a carboxylic, or may have a phosphate group, or sulfonic PFAS types. And when we think about the source of PFAS, those are like everyday products that we use, which could be packaging products, or our like water resilient materials, and also the ones which we use in our kitchens. Some of them have this non-sticky behavior, which came from this PFAS, from the use of these chemicals. And also commonly we find these chemicals in firefighting foams and stuffs. And when we see their health issues, or the health risks from these chemicals, we may have like neurotoxicity, high cholesterol, liver damage, and also a kidney cancer. Some of these are highlighted in previous studies. Here, I want to just briefly see what are the PFAS removal techniques. We have destructive techniques, which are basically focusing on degrading the carbon to fluorine bond and changing these PFAS compounds to different materials, less harmful, saying in quotation, which is like could be fluoride, or it could be carbon dioxide and mineral acids. But of course, since they will degrade, and which will enhance the degradation of these chemicals from our environment, they are the best technologies, but the drawback for these technologies is they are highly costly in their, and also some of them are in development stage. When we compare to the non-destructive ones, the level of technology is higher and their applicability is, or the conventionality of these techniques is less, and also they are costly and high energy demanding. And the other one is non-destructive techniques, which are basically focusing on separation of PFAS from our contaminated water, and may have like membrane filtration, foam fractioning, or the commonly used one, which is activated carbon, or another, the one which I'm focusing ion exchange resins. So they basically involve on separation of PFAS from the contaminated water, which is cost effective, and the conventionality of these techniques is higher. But the issue with this one is we need to deal with the materials that we removed, the PFAS compound or the concentrated PFAS compounds in these materials or in these adsorbents that we have used. So for my study from these different techniques of non-destructive, from the different options of non-destructive techniques, I will be focusing on ion exchange resins. Here, I just want to show how ion exchange resins work. So we may have like a cation exchange resin or an ion exchange resin, which the polymeric backbone could be like for cation exchange resins may have like negatively charged functional groups, and the other one in an ion exchange resins may have like a positively charged functional groups. And in our water, we may have like the anions, cations, and also anions. Like for cation exchange resins, we have, for instance, calcium, magnesium, and other cation ions in our water, and it works with it changes with the polymeric functional groups, which may attract those anions and exchanges with sodium. Excuse me, I think I missed. Yeah, so which exchanges with this, these cations or anions will attract to the polymeric functional groups, because we said for cations we may have like negatively charged like sulfonates, which will attract these cations to their surface and will exchange with the sodium ions we have on the upper boundaries of these resins. And during regeneration, we may have like sodium chloride as a salt, as a regenerating salt, and it will counter ions will exchange with already, let's say, after we removed those inorganic ions in our water to these resins, we can regenerate again for the second cycle or third cycle use of these resins by exchanging the sodium or chloride ions, depending on which type of resin we have, and will replace the already adsorbed ions on our surface of the resins. Besides these ion exchange conditions, we may have also other adsorption mechanisms for PFAS on resin-based adsorbent, which could be like the one we have seen earlier. Resins having quaternary ammonium groups may have like ion exchange interaction with the anionic head of PFAS. And there is also another attraction, which is hydrophobic interaction between the nonpolar tail, or the longest one, the carbon fluorine bond, the tail of the PFAS with the surface of the adsorbent. We may have hydrophobic interactions, and also, even though the strength is here on the left, I have shown the strengths of these intermolecular forces may be like lower compared to the ion exchange, because the main interaction is ion exchange, but also we may have van der Waals force interactions between the PFAS tail group and the adsorbents. When we say about in the study, I said I will be focusing on the use of ion exchange resin in RSSCTs, right? So RSSCTs are just a scaled down version of pilot or full scale columns. And here I just want to briefly show so we have like a full scale column, which shows real world performance and also considers biological activity because it takes longer time, which will show the real experience, why what we have in our water treatment facilities. But the other drawback or disadvantage is it takes longer time to get the results and large volumes of water and high cost, whereas the pilot columns are a scaled down version of these full-scale columns, which gives accurate prediction of full-scale performances, but still longer time, which is less than full-scale, but compared to the RSSTs, we still have to face with long time to obtain those results and large volumes of water used for these tests. But when we see RSSTs, they predict pilot or full-scale performances and just gives results in a couple of weeks and the cheapest options. But maybe the drawbacks of these RSSTs may not count biological activities, so because they are very quick and we may not see what really happens. We may miss some parts what we may see in our real-world experience. For RSSTs, scaling, because since they are scale down versions, we need to scale up. We need to scale up those RSSTs, or when we design them, we need to scale down from an existing pilot column, or it could be full scale column based on different assumptions. So we have like two assumptions which were provided in studies. That's either it could be proportional diffusivity approach or constant diffusivity approach based on the assumptions, because the proportional diffusivity approach assumes intraparticular diffusivity is proportional to particle size, whereas the other one doesn't consider that this diffusivity really do not change with the particle size. And depending on these values, we can decide which approach we are considering for our studies. And the main governing parameters are particle size, empty bed contact time, and hydraulic loading rates. When we compare pilot scale versus RSSTs, of course, since we are using these very tiny columns, the main changes in particle diameter, because we need to scale down to the RSSCTs models, and which involves grinding, right? So we have these spherical beads of resins, but we need to grind them to fit to those particle sizes that we have designed for these RSSTs. So my research motivation is because we have seen that we need to grind those beads to fit to the RSSTs, but then I researched or I reviewed some of the literatures which are related to ion exchange resins with which applied RSSTs on PFAS, RSSTs for PFAS adsorption. And from that, there are very limited studies on application of ion exchange resins. There were about 8 to 10 studies, which at the time of my thesis preparation. And from those, only few studies have specified which grinding techniques they used, because most of them, they didn't really, because that wasn't the main topic of these studies, or the main objective of these studies. There wasn't any highlight which type of grinding techniques they used, of course, but we know at which size those studies were studied. But only few have reported those, and from those, some of them have used blender grinding, and the other one used mortar and pestle, which is a common way of grinding adsorbent materials. But from these studies, I have seen that the prediction accuracy of RSSTs compared to the pilot scale performance have some discrepancies. Like in Schaeffer's, it was reported that it was 100% or almost perfect prediction accuracies were observed for RSSTs up to 20% of breakthrough profiles. And in the other study, it shows that the breakthrough prediction of contaminated groundwater with PFAS was underestimated almost by 30% on average when we compare the RSSTs versus full-scale performance. So there could be different reasons which were studied in those studies, which were related why we are seeing these discrepancies in the prediction accuracy of RSSTs, specifically for ion exchange resins, because there is plenty of studies for activated carbon, but there is a limited ones, and from those, most of them have focused on the modeling approach or other techniques to study why we have seen these discrepancies. But in terms of the way we grind, or if these grinding techniques that we are applying for these resins have any effect on their physiochemical characteristics or in their adsorption profiles, it wasn't studied. So that was the motivation of my thesis research, to study like what would be the effect of grinding techniques on the adsorption profiles or adsorption of PFAS or breakthrough profiles of PFAS. So saying these main objectives were to examine different grinding techniques. So in the previous studies, we have seen there is a blender grinding, also mortar and pestle, and ball milling, which was not in resins, but there was it was applied for activated carbons. And then with those ones, I have added two other grinding techniques, which is one is a two-step one. First, freeze drying the resin bits and then blending them, and the other one is jet milling. So having these 5 different grinding techniques was tested for 3 types of PFAS, carboxylic PFAS, PFPA, PFHXA, and PFOA in RSSCTs. And also I have the other aim of this study was to evaluate the role of resin preparation in the accuracy of adsorption predictions. So for this, I have used a PFAS selective ion exchange resin, which have macroporous polystyrene cross-links with divinyl benzene polymeric structure, and which was the reported exchange capacity was almost 0.9 milliequivalent per milliliter for these resins. Like I said earlier, there were 5 grinding techniques applied, and all of them have passed through wet sieving. So just to highlight like how these grinding techniques were applied. So we have just for blender grinding, a commercial coffee blender. I've used those ones. And for freeze drying, there is a freeze dryer, which the goal was to remove the water without damaging the chemical structures of the material. And the sample is almost cooled in for the water to turn to the ice, and it was vacuumed with low temperature. And then for ball milling, I have grinded with tungsten carbide balls, which are almost like 11 millimeter in size. And it was like milled with those balls to reach to this to the desired particle size. And for jet milling, which involves like a high pressure compressed air, which to create a high velocity between these particles, and during the collision, the particle size reduction happens. And I did that. I cooperated with another company for jet milling to get us the resin bits grind into the specified particle size. Then after that, all of them have passed through a wet sieving with one US mesh 140 and 170 to reach to almost 100 micrometer size. And since it was a wet sieving because I packed my columns based on mass, then I freeze dry all the samples and have done the experiment. So as I said earlier, 3 PFAS types were studied for this research: PFPA, PFHXA, and PFOA. Here I just want to show, because since I have 2 objectives, one is related to assessing the impact of grinding just in RSSCTs, and the other one is to see the prediction accuracy, of course. So I have a bench scale pilot columns, and the RSSCTs were scaled down. The RSSCTs were scaled down from an existing pilot column to this size, and then the pilot scales were scaled up from the RSSCTs. And here is just on the left to show the RSSCT setup that I have, and on the other side, the pilot scale setup. And just to highlight, like the adsorbent mass was almost 260 milligram for RSSCTs versus almost 93 milligrams, 93 grams for pilot scale columns. And from those 2 approach, diffusivity approach for scaling up these RSSTs. Constant diffusivity was used because that was the ones which were like from the different studies that I have assessed in the literature review. That was the ones which have a better prediction accuracy compared to the proportional ones. So I chose the constant diffusivity one. And since the study was done in both DI background and simulated groundwater background, for the simulated groundwater, I used not these compositions from a given research, and I simulated this groundwater in the lab and assessed the experiment to see the effect of adsorption in this background. So besides these compositions, there was also natural organic matter, which was added to this. Then the other one is characterization of these ion exchange resins, both the grinded ones and the ungrinded, the main bit. So there was ACM scanning electron microscopy have done, and also to understand if the grinding technique have influenced the morphological characteristics of these resins. And there was also FTIR analysis was done with FTIR to identify functional groups, and if we lose any functional groups during the grinding techniques or during the sieving process, and XPS to see the surface elemental compositions, and also the tau potential analysis to identify the surface charge. And the other characterization was done for water retention capacities. And it was done following a previous study by Cheng and Clamp paper. And here are the parameters that were used for both ungrinded and grinded resins, and which the steps that is passed through the different solvents to estimate the water retention. So after passing through this up to the sixth step, then water retention capacity was assessed by, then after passing through this, I dried it, these resins, then wet mass versus dry mass, I found the water retention capacities. Then the last one is total anion exchange capacities. The same paper was reviewed for this study, and after passing the sixth step, which is the last step, is to the seventh step, with passing the potassium nitrate. In this case, the concentrated potassium nitrate. So the nitrate will replace the chloride, because up to 6%, the sixth step, those ion exchange resins have chloride, and but on the seventh step, passing the potassium nitrate, the nitrates will replace the chlorides, and based on that, I identified the ion exchange capacity of those grinded resins as milliequivalent per milliliter per bed volume, so which is per milliliter. But in the previous one, when they are at the fully in chloride form, then those were dried, and then the wet mass versus dry mass was used for water retention capacity. Here, then after passing all this process, then here I will present the resulting discussion part. So for surface morphology of ion exchange resin before and after grinding, here we can see the ungrinded, which is a perfect spherical shape of these beads versus the different grindings. One thing that I didn't highlight earlier, I used these abbreviations, which was listed in the materials meter. So the one FG and PG is the one, the two-step one, freeze drying and blender grinding one. Then we have blender grinding, mortar and pestle, ball milling, and jet milling. To be honest, from this, there are, in some of them, there is like a sharp edge, and some of them are like kind of like less sharp edge, but we really didn't see a significant change in the surface morphology of these grinding techniques. And most of them looks like they have there is no really significant change that we can say based on this characterization. So the surface morphology wasn't really changed among the grinding techniques. Of course, it already lost the spherical shape. When we see the functional groups or the results from FTIR, so here I just want to show the absorbance versus the wave number. So here is for the ungrinded beads. So the beads that we get from the manufacturer, which have the hydroxyl groups, and also the TH stretching groups, and also we have the carbon nitrogen stretching bonds, which comes from the amine groups, and the CH3 which is coming from the groups of methyl amines. But then here I want to show if any of these groups if we see all these groups in the grinded ones. And from this result, we have seen that almost all of them have shown the same functional groups compared to the ungrinded or the original beads, which gives us yes, while grinding, we didn't really lose a specific functional groups, which is then whatever discrepancies we are seeing through our results may be due to other mechanisms. And here, from the for the surface elemental compositions, we can see that there is, for ungrinded versus the grinded ones, almost like the chloride signals the chlorine signals were doubled in all treated samples, which reaching to about 4%. It may show that while grinding, we have more accessibility for chloride counterions, or it shows enhanced exposure of exchange sites. And we see also one thing to highlight, maybe there is a significant decrease in oxygen content, which could be related to it may be due to the loss of weakly adsorbed surface moisture or oxidized functionalities on the PFAS from the PFAS compounds while grinding. But compared to the others, we have seen that the ball milled ones have exhibited a bit higher compared to the other ones. And this may influence on the results that we are seeing, which may have an effect on the adsorption capacities. And from the zeta potentials, there is no statistically significant difference between these grinding techniques, but we have seen there is a lower zeta potential for the ungrinded, but which may be related to while we do the experiment, since they are large beads and they are less they agglomerate, and which leads to the low zeta potential values during the experiment. And from the water retention capacities, we have seen there is a significant drops from the ungrinded one versus the grinded one. And from previous literature, the higher the water retention capacity have, the higher the mass transfer for PFAS within the resin, and it will lead to faster adsorption. That was the assumption. And to be honest, the difference among the grinded resins was not that much, but we see some differences. So the expectation is the ones which retained as high as possible for the original beads have higher PFAS absorption compared to the ones which really lose the water retention capacity significantly. And here is the result for anion exchange capacities, and it wasn't really a significant difference or between these grinding techniques. So we have seen some differences among them, and because this may have influence on the RSSTs experiments, as let's say the short chain PFAS have more effect on exchange capacities compared to the long chain ones. So this may slightly impact the adsorption capacities, but on characterization side, it was like comparable differences. Then after this, I'm gonna show the breakthrough profiles of the RSSTs and also the pilot scale columns. So just to give an idea of how I'm going to present. So for any breakthrough profile, we have like C over C nodes, the initial versus the concentration at a given time versus the bed volumes of water treated. And from here, I'm gonna show them. I will be highlighting the ones at when it reached to 50% adsorption or bed volume 50, where C over C node reached to 50% or half the breakthrough profiles. So from here, we can see that for PFPA, the freeze drying and blender grinding have like highest bed volumes treated compared to the other ones, which could be though there is a very small differences in ion exchange capacities, but maybe compare not only the ion exchange capacity, it may have other molecular interactions happening, but that may have an influence on the adsorption profiles of this PFPA. And for PFHXA, we have seen a different trend compared to PFPA, which is jet milling have higher adsorption, higher bed volumes treated compared to the other ones. But from here, we can, the typical key takeaway would be like as the chain length increases, there is higher bed volumes of water treated from bed volumes of water treated in these RSSTs. And for PFOA, we see that ball milling have higher BV50 treated compared to the other ones. And this, like I highlighted earlier, there is oxygen values for when we see the surface elemental compositions in the XPS analysis, where like it was a kind of a little bit higher compared to the other grinding techniques. And this could be like, it may retain the hydroxyl groups of the resin a little bit compared to the other ones. And this may have an influence on like on the PFOA adsorption, though the PFOA adsorption is more highly relying on hydrophobic interaction, but we may also, besides hydrophobic interactions, there is also a hydrogen bonding, which may enhance the PFOA adsorption for ball milling. That's the assumption I have, seeing the results that we get from the RSSTs breakthrough profiles. So looking at after the DI background, the next step was to do, so I have tested 3 PFAS types for DI background, but then I picked 2 of them, PFPA and PFOA, in simulate to understand if grinding techniques have influence on the adsorption profiles of short chain and long chain PFASs. So in both RSSTs and pilot columns. So here the first one is addressing the first objective, which is breakthrough profile of RSST for PFPA in simulated groundwater. And here we can see like there is, of course, a high drop on the bed volumes treated due to the competition between the inorganic anions and the PFAS groups. And still we are seeing freeze drying and blender grinding, and also mortar and pestle have kind of a similar trend, exhibiting a higher bed volumes treated compared to the other ones. But there is a huge drop, which is matching with previous studies that PFPA is highly impacted by the presence of inorganic ions or the groundwater backgrounds. And compared to single solute system in PFOA, we are seeing some difference. Of course, there is a little bit drop down, but we didn't see highly, like, which is about 50% in PFBA, but here it's less than 25% decrease in bed volumes treated in the case of PFOA, comparing multi-solute versus single solute, because due to the fact that natural organic matter is like less affecting for long chain PFAS, because the main interaction happening is hydrophobic interaction compared to which is not really impacted by ionic inhibition. And here we see that mortar and pestle shown higher bed volumes treated compared to the other ones. Then, so in the first objective, so the main, like I said earlier, the motivation of this research was to understand if grinding techniques or the way we prepare these materials have an impact on the absorption profiles of these PFAS groups on RSSCTs. And also the second objective was to understand if any of these grinding techniques have influence on the accuracy of prediction accuracies, on the prediction accuracies of RSSCTs when we compare to pilot column tests. So in the first one, we have seen that there is a difference in the bed volumes treated depending on which kind of material preparation we have considered for the RSSCTs. And here I'm going to show in DI background and also in simulated groundwater for pilot columns on the left side, and then the correlation between RSSCTs versus pilot columns to understand the prediction accuracies. So from here, for PFBA in DI background, the one which is in golden color, the one you are seeing, the additional one compared besides the previous 5 breakthrough profiles. The golden one is a pilot column, and when I compare the correlation between RSSCTs versus pilot columns, I have seen that freeze drying and blender grinding have higher correlation versus the other ones, and the other ones following the presented trends. And this could be related to that these 2 steps have retained the structures of these resins, and also may have more exchange capacities, which is the main interaction that's happening for short chain PFAS like PFBA. That's why we may see a higher correlation compared to the other ones. And for PFOA, we have seen that jet milling have highest prediction accuracies compared to the other ones, and this could be related to the preserved. When we see the water retention capacities, jet milling have retained closest to the ungrinded one, and this may have later on influence on the adsorption capacities, which may enhance its adsorption capacity. But one significant thing that we take away from this research is like we are seeing differences also in prediction accuracies depending on which type of grinding techniques we have applied. Same here for PFBA in simulated groundwater. Here the trend is reversed because like jet milling was higher here compared to the one we are seeing in single solute. Freeze drying was the highest, and this maybe contributed to like the presence of competition between anions and PFBA in the resin. And we are seeing, less prediction accuracies compared to the single solute background when we compare the RSSCTs versus pilot columns. And for PFOA, we are seeing mortar and pestle have highest prediction accuracies with 96% almost compared to the other ones, and it have different profile as well. The trends are different while we are seeing in DI background and simulated background when we compare which ones predict more accurate from those 5 grinding techniques we have applied. So to summarize the key findings, so from the SEM analysis, we have seen that there is no a significant morphological differences between the grinded samples of the resin. And in the FTIR analysis, we have shown that it retains the same functional groups as the ungrinded or the original resins. In the XPS analysis, surface elemental composition have shown there is a little bit differences compared to like the chloride, of course, content is high. It increased in grinding, which shows there is more accessibility for the quaternary ammonium groups, but we have seen a significant decrease in the oxygen content. So we have the difference among the grinding techniques were not that much, except ball milling one. And surface charge, it became more negative after grinding due to increasing surface area and exposure to functional groups. And when we see water retention capacity and also anion exchange capacity, for water retention capacity, there is, yes, a significant decrease, which may be related to pore collapse or which decreased from the original resin, whereas in anion exchange capacity, the difference is not that much among the grinded ones, but we are seeing a little bit differences in this ion exchange capacities. So when we see the resin preparation versus breakthrough profiles, the key highlight is, yes, resin preparation methods significantly influenced the breakthrough profiles of both short and long chain PFAS in RSSTs. And just the last note is to say that from this study, which we used a high concentrated PFAS, which is about the one I have shown earlier in material and emitter, which is like about 50 ppm as a starting concentration of water. The BV50s, when we compare the BV50 for these different adsorption profiles of these grinding techniques, freeze drying and blender grinding have higher bed volumes treated in both water matrices for PFPA, whereas in PFOA, ball milling was highest in DI and mortar and pestle was the highest in simulated groundwater. And here is just to show that which one have highest prediction accuracies regarding PFPA or PFOA under DI background, which is freeze drying was almost higher with 91%, and jet milling was almost 94% for PFOA. But in simulated groundwater, we have seen that jet milling have higher adsorption capacity prediction, and for PFOA it was mortar and pestle. And grinding techniques that reserved the water retention capacity closest to the ungrinded resins, they have demonstrated a better prediction accuracies for PFOA, which we see for jet milling, which is 94%. And effect of natural organic matter is less in long chain PFAS due to that ionic inhibition is inversely related to PFAS hydrophobicity. And the other keynote is choice of grinding techniques significantly influences both PFAS absorption and reliability of RSSTs for scaling up to pilot applications. Here, I just want to mention some of the limitations of this study. As I said earlier, PFAS concentration were significantly high compared to what we really see in real environmental conditions. But the reason was like, we wanted to see, okay, yes, it's higher than the environmental conditions, but we wanted to see if our motivation or if the grinding techniques have impact or not. So if we make the concentration the same for all grinding techniques, then whatever differences we are seeing among those the breakthrough profiles is related to the other mechanisms, not maybe the concentration of PFAS. But that's a limitation. We don't know what happens in lower concentrations or in real environmental conditions. So that's one of the limitations. And also, I use synthetic water, simulated groundwater instead of real actual groundwater, which may exclude some complex matrix, what we may have seen in actual groundwater. And for this research, the study focused only on carboxylate PFAS compounds, limiting the findings to apply only to those, because all whatever difference we have seen here only applies for carboxylate, and I didn't really address for sulfonate ones. And also I may have one of the limitation could be considering other parameters for comparison, which could be DOC level and SUVA values, if grinding techniques also have influence on these characterizations. So future work that we are considering in our research group is like really to address those limitations, to conduct experiments at lower PFAS concentrations and consider real groundwater samples, and also assess the other sulfonated PFAS compound like PFOAs, because we have also the one a regulated one, which is which could be considered in the future work, and also considering other characterizations besides absorption profiles. I would like to acknowledge Dr. Mahmoud Irsan, which is a project PI, and also my advisor, which really helped me to assess all my research, and also in the master's program. I'm really grateful for his guidance and his encouragement, and also my research lab colleagues, which really helped me during assessing this research. UND College of Engineering and Mines, Department of Chemistry, Physics, and Biomedical Science, because I have conducted XPS analysis, SEM, and also zeta potential in coordination with those departments. And just this SEM imaging was done with biomedical sciences. And if you want more information about our research group, you can check Irsan Research Lab with this QR code. And of course, I really want to thank WQRF for giving me this chance to present my research on this webinar, and also for organizing the poster competitions to showcase my research. And I'm really thankful for the opportunities. Here are some of the references I've highlighted during the slides. And thank you so much.
Thank you. So if you guys have questions, please put them in the Q&A box. And while you guys are typing those up, I have a few reminders. A follow-up email will be sent after the webinar with a link to the recording. And additionally, if you are WQA certified, you can earn 0.1 CPD by attending this live presentation. So now we can begin Q&A. Our first question is, what is the average particle size of the resin after ball milling?
Okay, yeah, so for all of them, like I will, excuse me, it's about 100 micrometer, because I make those like for column design. Here are for all grinding techniques that pass all grinding techniques. After wet sieving, I managed to have this particle size, because all of them were sieved between 140 and 170 US mesh size. So it was approximately 100 micrometer. And of course, I measured also those in SEM, and it was, we can see from the scale, they are about 100 micrometer.
Thank you. Another question we have is, did you observe the grinded resin experience more swelling when you dry it or heat it up compared to the non-grinded resin?
Yeah, but when we say swelling, it's reflected on the volume, right? So yes, like I'm not sure how to answer that one, because we have measured the water retention capacity based on wet mass versus dry mass, not on volume. So yeah, I need to look at how I did that. Yes.
Okay, thank you. Another one is, have you studied the scaling factor of RSSCT to compare pilot?
So for RSSTs, we already chosen which type of diffusivity approach that we are using. So from those, there are two of them. So I use constant diffusivity. It means I know the size of, I just want to refer. So there is here particle size for large column versus small column, and this equation, based on this equation, there is an existing pilot column which have the particle size and also hydraulic loading rates. Based on that, I scale down to the RSSTs that I want. So I say, okay, I'm gonna have 100 micrometer size. Then based on that, I calculated the empty bed contact time and how much could be the size of the RSSTs. So that's how I did the scaling up conditions for RSSTs to compare with a pilot one.
Thank you. What in your academic career led you to this area of research?
Yeah, so from like as a civil engineer, we have like different dimensions that we can specialize, but I was more interested with environmental aspect of civil, and I was working with my advisor and which works on which really interested on assessing emerging contaminants, and it was really, to be honest, I didn't have that much idea about PFAS before joining this research group. I didn't know they were really alerting emerging contaminants, and I learned about them, and I was more interested on how to treat them, and also about this RSSTs were really fascinating one, just to understand that, oh, we can really scale down to those columns instead of doing pilot columns, even though we see discrepancies in prediction accuracy, still those needs to be studied more, how to improve the prediction accuracy, but it's really an interesting thing that we can cut the cost that we use for testing different adsorbents. So I work with him and I got more interested in emerging contaminants, and I found myself, oh, let's do my thesis on this topic.
Awesome. Someone wanted to confirm that there is no major difference in particle size among the different grinding methods. Is that correct?
Yes, because they all passed in the same sieving process, in the same mesh sizes, and also from the ACM analysis, we see that this when we check the scales, they are almost the same.
Perfect.
That's how we control for the particle size, because like there are plenty of experiments that have been done. So the approach that we can consider to have the same particle size is passing them with the same ways of sieving and also drying technique, which is all of them were dried with freeze drying, and all of them were packed on the RSSTs based on mass. So
thank you for confirming. Are you or anyone at the university continuing this research?
Yeah, for now they are. I have graduated and got a job, so but they are. My research advisor is considering to do experiments on at lower concentration levels, and also we are working on writing paper on this research.
Last question. How was your experience interacting and presenting with the water treatment professionals at the WQA convention?
It was really nice. It was my first time to really meet from industries, and I have visited to some of the booths just to see like about their work, and I was so happy. Some of them, especially on the last day, they came and tried to understand about my work and questioning critical questions, which I took those to consider while writing my research paper. And so it was really nice, and I was very interested in our interactions.
Thank you. That's good to hear.
Actually, one thing to mention, I got also, sorry, I interrupted you. There was someone who approached me. There are also some small resins that could be that were used for different purposes. So we interacted and also send us some samples. So we are doing some research if it just with those small resins versus the grinded ones to understand. That's another part of the research. So it beyond having the interaction, it also led to adding a topic or like a portion to my study, broadening my studies. So it was really a good one.
Yeah, that's an awesome connection. So thank you for all your great questions today. If you have additional questions, you can email us at foundation@wqrf.org. And then if you are a student or you know a student who may be interested in submitting a poster session for our 2026 poster contest, be sure to check out our call for poster abstracts that's on our website and our social medias. Submissions for this are due December 31st. So thank you for joining our November webinar special, and we hope to see you next time.
Thank you so much.